Welcome to the Bitcoin Unlimited podcast. My name is John Moriarty, and today I'm joined by Jonathan Toomim, an independent Bitcoin Cash developer who's been working on Bitcoin since way back in 2015. Jonathan, thank you for joining me.
Thank you. My pleasure to be here.
So I'd like to focus today on your work scaling Bitcoin. And while, of course, we'll get to the work being done on that front nowadays, you were working on-chain scaling since pretty early on, weren't you?
Yeah, so I think I started working on Bitcoin with Gavin and Mike, Gavin Anderson and Mike Hearn in 2015. But the work that I was working on was the mempool eviction code. At the time, Bitcoin was expecting that blocks were about to start getting full, and there were a few different ideas for how to do that mempool eviction. And I was working on the XT approach, which was to do random eviction so that the set of all nodes on the network would have a distributed set of transactions. So that's not exactly scaling. That's a little bit different. But shortly after that, I got involved in Bitcoin Classic, and that was more directly scaling involved.
Well, if you don't mind, I'd love to hear about if there's a short story of it. What was the benefit of having the transactions be actually not synced across mempools in that case?
Yeah. So the idea was that if every node has, say, 100 megabytes of RAM available for storing transactions, then you could either have all of the nodes store the same set of transactions, or you could have all of the nodes store different sets of transactions. And if they're storing different sets of transactions, then the distributed copy has a lot more than 100 megabytes of space available. Like you can use, a different 100 megabytes of transactions for each node, or you can have an overlapping set. And this was before the fast block propagation methods had been developed. So at the time, there was no utility to having syncing of mempools, except insofar that it would prevent the transactions from being double spent as easily. And so if we had maybe twice as many total transactions in the distributed set as there was room in a single node's mempool, then somebody who created a double spend transaction would have a 50% chance of getting it into each node. That was going to be the degradation cost. Bitcoin XT also added a method of sending, whenever they saw a double spend transaction, they would rebroadcast the original transaction followed by the double spend as a way of trying to announce to other nodes that there was a double spend in progress. So that issue is we were trying to take care of that issue in a different method.
Very cool. It is interesting that it seems like a whole lot of effort was put into dealing with the repercussions of full blocks, wasn't there?
Yeah. I mean, it was something that we knew was going to happen. It was basically what the Bitcoin core developers and also Bitcoin XT developers were trying to fix in 2015-ish. The mempool code and the eviction code and the block template code were being rewritten largely from scratch in order to design a new system that would perform better in high throughput scenarios. It's actually kind of interesting. This random idea, this distributed idea, is something that I've been thinking of trying to resurrect, not for mempool eviction, but for transaction relay recently. One of the bottlenecks that I've seen in the current code is with transaction relay. Often we will saturate the capability of a TCP connection with high packet loss and high latency to relay transactions between nodes. And over each connection, you can sometimes get, if you have like 5% packet loss, you can get about 200 transactions per second through that connection. It doesn't matter how much bandwidth you have. TCP itself limits it to about 200 transactions per second. And right now, Bitcoin, ABC, BCHN, Core, that family of nodes always relays transactions in the same order between any pair of nodes. So even though you might have 50 connections, you can only get one connection worth of transactions through those 50 connections. But if we did like a more randomized relay pattern and added some noise in terms of which transaction gets selected for relay first, then we could actually get closer to 50 connections worth of transactions through. So yeah, I think there's a lot of interesting applications of that random transaction selection idea, even in different contexts.
And just for people listening along who aren't familiar with it, and that actually includes me, TCP, that's an internet protocol. Is
Yeah.
that right? Just a way that computers talk to each other over the internet.
Yeah, so TCP is one of two most common protocols on the internet. It's the most common for the underlying transport of network data. So you might have heard of HTTP or HTTPS. Those use TCP on the lower level. And TCP is designed to provide a stream of reliable data. TCP is supposed to take care of all of the issues with packet loss and with breaking up messages into smaller chunks so that it can be fit into a single IP packet, and also congestion. TCP is supposed to detect congestion and change the transmission rate to stay below the point where the pipe gets saturated. And TCP works pretty well in a lot of circumstances, but the algorithm that it uses is not very high performance and often can mistake, or will always mistake, baseline packet loss as a sign of congestion. So whenever there's packets being lost because the network is unreliable, TCP says, oh, the network is congested, I'm going to reduce the transmission throughput rate. And this is particularly a problem when communicating between China and the rest of the world, because those internet connections are always very lossy. Sometimes, like when I was testing this a week ago, I was measuring around 50% packet loss to Yoku.com, to one of the major Chinese websites. And it usually varies between about 5% and 50%, 5% and 30%, something like that. And so that basically makes TCP not work very well. And it's a particularly big problem for Bitcoin because the majority of mining is actually done in China. So in order for, if at that point, once the majority is in China, that means that this is now the rest of the world's problem just as much as it's China's problem, because it makes it so that people outside of China have a difficulty mining profitably, and people inside China have an actual advantage over non-Chinese. So, so yeah, that's one of the big problems of Bitcoin scaling right now. It's trying to figure out how to make Bitcoin perform even when you have a lot of your TCP connections be lossy, and when you might even have an island, so that you have one subset of nodes that are connected to each other very quickly, but outside of that island, you might have a different island, or you might have multiple continents of nodes that can't connect to that island in a fast and efficient fashion.
And so is that where tools like XThinner come in? Is that what helps with the TCP issue?
Yeah. So XThinner is one way of solving, or one way of addressing that. BlockTorrent will do a better job of that, but I think actually the best way to address that issue is probably the next thing that I'm going to be working on after I finish this mempool code that I'm working on. But instead of using TCP, to switch to a protocol called KCP. And KCP is a relatively new protocol. It's not built into the operating system, unlike TCP and UDP. And KCP was designed basically from the ground up to deal with the problem of communicating in a fast, low latency fashion in high packet loss environments. It was basically, you can even say that it was written by Chinese people in order to bypass the Great Firewall of China and get like YouTube and Netflix over VPNs with good performance. That was kind of like what it was designed for originally. And because of that, it has a lot of really good features for what we want to do. It has optional built-in encryption, so we can encrypt the data stream to prevent man-in-the-middle attacks, which is kind of a nice bonus. And it allows us to either use KCP's congestion control algorithm or to override it, depending on what we want. We just flip a switch in the code, and we can choose what we want to do with that. We don't have to follow the TCP congestion control. And it also contains a feature called forward error correction, or an erasure code. And that's a way of adding additional packets to the data stream that give us information so that if some of our packets are missing, we can reconstruct them given the extra packets. So we might say, if we have 10 packets worth of data, we can send 15 packets or 12 packets or 20 packets, up to you, up to the programmer. And if any of those 10 packets make it through, then you can reconstruct the original 10 packets. You don't have to have the exact original 10 packets. You can get, you can miss packet 3, 5, and 7 and still reconstruct those based on the extra packets that you send at the end. And that allows you to deal with packet loss in a much more efficient fashion because you don't have to wait for retransmission. You don't have to wait for extra round trips. You don't have to wait for timeout for, you don't have to wait a certain amount of time to say, okay, I was expecting this packet to arrive within this time window. It hasn't, so I'm going to request the retransmission. You don't have the risk of that request for retransmission also being lost. And so it gets rid of a lot of these really pathological cases that you can often get with TCP. So KCP, I think, is going to make a huge difference to this once I get around to adding it, or somebody else gets around to adding it. XThinner was a different way of addressing this problem. XThinner's approach, though, was just to make the amount of data that you have to send smaller. XThinner gets about 1/4 or 1/3 as much data for a block transmission as compact blocks does, the previous most common used protocol. But XThinner and compact blocks require that all the transactions have already been transmitted and already been received by the other node. And that means that if the bottleneck is at transaction propagation and transaction relay, XThinner and compact blocks don't actually help. Fortunately, so far, it seems that we're able to maintain good transaction throughput. The bottlenecks that I've seen for realistic network-like, worldwide network-like conditions have been showing that we can get up to about 200 or 300 transactions per second broadcasting before we start to run into problems with a network that has about 5% packet loss. And so far, we've only been doing 100 or so transactions per second. So we haven't actually seen that issue on mainnet. But the problem is that as soon as we scale above that, we're going to run into that. And that's actually a limitation that I found fairly recently. I didn't realize that was going to be an issue until like a week and a half ago, I think, when I got my test set up for doing emulated packet loss running. So yeah, XThinner definitely can help, but there's another issue that I found during the testing of XThinner that is actually what caused me to decide to fix the 50 transaction chain limit. Sorry, I'm going down kind of a second rabbit hole. I haven't even finished the first rabbit hole. There are too many rabbit holes in Bitcoin. That's kind of the problem that I've been
That's all right.
into.
I think the rabbit holes are fine, so we can dive into them, and I'll do my best to keep track of any we haven't finished, but please feel free if you'd like to dive into that. One thing I'd like to come back to is, where the other bottlenecks are and things like that. But for now, if you'd like to talk about what you just came across, I'm sure everyone would love to hear about it.
Yeah. So I was testing XThinner and trying to make sure that it was indeed faster than compact blocks. And one of the features that I was trying to get working was this feature that I call fast forwarding, or compact blocks calls high bandwidth mode. And that's the idea that you don't need to verify the full block before you relay it to the peer. If you receive the block via compact blocks or XThinner, all you really need to do is to verify that the proof of work is correct and that the proof of work covers the list of transactions in that block. So what you need to do is you take that list of transactions and you do the Merkle hashing algorithm down to get to the Merkle root, check that matches the block header, and then you hash the block header and check that matches the difficulty target. Those are the things that you have to do before you relay that block, and that's a much faster process than like checking every single transaction, making sure that it doesn't double spend, that it has correct inputs, that everything is signed correctly, etc. So you can skip all of that, or you can delay that until later.
Is there a technical reason that you draw the line there as far as what has to be done before relaying?
Yeah.
Or is that...
You don't want to be unwittingly helping somebody else with a denial of service attack. If somebody sends you an invalid block, and you broadcast it to everybody else, you're going to be wasting everybody else's CPU and bandwidth. So in order to prevent against denial of service, in order to protect against wasting of bandwidth and computational resources, you have to make sure that people have spent money and are invested in that block. That block is the result of at least $1 worth of computation, but in this case, a few thousands or tens of thousands of dollars of computation. So, but you don't have to do the rest, because if you're forwarding somebody else's, $5,000 block that happens to be invalid, you don't have to worry about somebody trying to saturate your bandwidth and CPU usage, because it's really expensive to spend $5,000 to use like 5 seconds of the network's resources. That's not a good deal. So high bandwidth mode and fast forward mode will do only those minimum steps needed to prevent denial of service before forwarding. And that can get like the latency for a worst case block down from, say, 5 seconds or so down to like 150 milliseconds for the quick check and then forward step. And that makes a big difference, because it's 5 seconds per network hop, 5 seconds of delay at each node along that block propagation path that it would otherwise be getting, versus 0.15 millis or 0.15 seconds. And that's the difference between a block taking around 30 seconds to propagate through the network and the same block taking about 1 second or 2 seconds to propagate through the network. And 30 seconds is definitely too long, but 1 or 2 seconds is entirely fine. And I was looking at this, and in my initial tests, I was finding that pretty much no matter what I did, it was always taking 4.5 seconds per hop for the blocks. And that was true both for XThinner and for compact blocks. And initially I thought, wait a minute, I thought that compact blocks was supposed to have this high bandwidth mode, and it was supposed to be enabled by default for 3 nodes, but it's not happening. And I was very confused by this. So I thought that if I implemented it in XThinner using a different path, that I'd be able to get it to work. I did that, didn't fix it. And I dug into this problem a bit more, and I looked through the debug logs with the logging of every single message sent over the network enabled. And I found that it was actually sending the compact block or the XThinner block before validation. But unfortunately, these blocks were often missing 1 or 2 transactions, which is supposed to be no big deal. The recipient node will say, hey, I'm missing these transactions, can you send them? Sends over a get block transaction request, and then that's supposed to be replied to with those transactions, and it should only take 1 round trip time and like 150 milliseconds, something like that. But this process wasn't actually working the way it was supposed to. That recipient node was detecting the missing transactions and was quickly creating the request and sending the request back. And the original sending node was receiving that, but it wasn't processing that message, because in order to process that message, it would have to acquire the CS main lock, basically like the big lock, the big mutex, the big thing that prevents Bitcoin from running multiple threads at once when they share this, or when they all need to access the same data structures. And this CS main lock gets acquired during block validation. And when blocks are being validated, it holds onto that block validation lock until the block is fully validated and until it's ready for the next block or the next set of transactions. And because responding to the GET transactions request was requiring that lock, and because that lock was being held as soon as, or like basically from the moment after the fast forward or high bandwidth mode block was sent out until the block has been validated, those GET transaction requests could not be fulfilled until after the block was being validated. And that was making basically high bandwidth mode not work at all.
Sure. And just and please go ahead and correct me if I don't have this right, but just for our viewers, so the idea of locking, what's happening is that the computer has access to a certain amount of data, and while it's working on it, you can't have someone else just come in and change the data, some other function, right? And
Yeah,
so what it's doing is that lock is telling the computer, I need this data, and I need it not to change until I'm done with whatever I'm doing. Is that about right?
yeah. Like, I mean, you've got like basically two hands of the computer, and you can often do like two things with two hands at the same time. But if you're trying to turn the same knob with two hands, it's not going to work very well. Also, if you're trying to change the knob with one hand, if you're just trying to check it with the other hand to see what the reading is, all sorts of weird things can happen. So Bitcoin's code um, basically has one big knob for almost everything. It has one lock that covers almost all of the major data structures, and that's the CS main lock. And almost everything that runs has to grab that lock. So like, and I've run into this problem a bit later when uh, I rewrote a little bit of the XThinner code to not require this lock for processing the get XThinner block transactions requests. And I did that and I tried it, and it didn't actually fix the problem. It didn't even make any difference at all. And what I realized afterwards was, so you have the blocks sent out, and then 150 milliseconds later, the get transaction request arrives. And in the meantime, the recipient, or the sender node has received a inventory message or a transaction message that preceded that get block transaction request. And all of the messages have to be processed in order. And processing the transactions requires the CS main lock. And so it can't get past processing the transactions, which means it can't even see that there's a request for the block transactions, which means that it can't fulfill that request, even though it would be able to fill that request if it could get to it. But it just gets blocked by the requirement for serial processing of networking messages. And like, when I ran into this issue, I was, you could say, a little bit frustrated. And it seems like there would be two paths to fixing it. One would be to like completely rewrite the way that the networking code makes assumptions about the ordering of processing of messages, and like maybe create a rule such that certain types of messages could be, you could peek through the queue and the message queue and pick out these like low latency flagged messages and process them out of order, make something like that happen. Or I could just fix the block validation and make it maybe 5 times faster. And I chose the second path. So
Gotcha. And so where did the block validation speed? That's something that's currently being worked on, that you've already been working on, or something we've already covered?
I kind of finished it. I wrote the code that makes block validation several times faster. It's actually not actually validation; it's block processing. But I wrote that code. It's in a work in progress merge request on the BCHN repository, and it turns out that the reason why this was slow in the first place was because of the child pays for parent big O(n) squared issue that causes the 50 transaction chain limit. So like, it turns out
it's in processing the transactions
yeah,
that were getting in the way. The ones that were getting in the way were child pays for parent relevant transactions that took a lot of processing.
yeah. I mean, it wasn't the child pays for parent themselves. It was the need to be able to, or the desire, or the plan to be able to handle those. It was the package the package handling code, the transaction package calculation code. The idea that you would want to take groups of transactions that are dependent upon each other and pay their parents, or pay inputs spent by the parents or whatever. Sorry, not describing that well. You're using a chain of transactions as a group of transactions and calculating the fee for the group versus the size for the group, rather than calculating the fee for the individual transactions. Or actually, you're doing both at the same time. And the algorithm that was being used for doing that was very accurate and is like theoretically optimal for making sure that you can get the most fees into a block when you're assembling a block. But it's also very slow. If you double the number of transactions in a block, or if you you double the number of transactions in that chain, then you quadruple the amount of CPU processing that it takes to calculate the fees and fee rates for that chain. And that issue where it's n squared makes a lot of things in the Bitcoin code very slow when you're dealing with long transaction chains. And it turns out that my test setup was using an average of about 26 transactions per chain or per package. So not quite the full 50. So it could actually have been about 4 times worse than it was. No, sorry, about 2 times as worse, 2 times as bad. Because if you double the length of the chain, you're getting twice as many transactions. So 4 times as much processing for twice as many transactions, so half as efficient. But yeah, so the 4-ish seconds that I was measuring could actually have been 8 seconds if I was using 50 transaction chains. Yeah, and that was too large, and I looked into the code for reasons why it was that slow and ways that we could improve it. And I noticed that it was doing a lot of processing. Say I had a 32 megabyte block, 105,000 transactions. It was doing a lot of processing on those 105,000 transactions, even though those 105,000 transactions were being removed from mempool. It was doing calculations, needed to make sure that each one of them had the right fees and package fees and stuff for the next time they might be included into a block, which was going to be never, since they had just been included into a block. So I changed the code basically to take like the transactions in mempool, and then take the transactions in the block, and remove basically all the transactions that were in both as a batch, and then for the ones that were remaining, only do those package fee calculations on the remaining transactions, instead of doing the package fee calculations on all of the transactions one by one as things were being removed. So like each time if you've got a chain of 5 transactions, and you remove the first transaction from mempool because it gets confirmed into a block, then normally you'd want to update the remaining 4 transactions to show them that like the package has changed. And you'd go to this one and say, hey, you need to calculate your ancestor information has changed. So it removes that one, and it goes to the next one, removes that, etc. So you do like 4 operations there. And then if you remove the next one, you do another 3 operations, and you move the next one, another 2 operations, and the next one, another 1 operation. And you remove the last one, you've removed all the transactions, and you've done 5 plus 4 plus 2 plus 2 plus 1 operations, and you have nothing to show for it because you've removed everything that you modified.
And that's only left over from the fact that there was code that ran when a transaction was removed from the mempool?
Yeah, it was the fact, basically the issue is that when I think it was Suhas Daftuar was writing this code, he programmed it to be incrementally updating instead of batch updating. And it's usually easier to follow incrementally updating code and to make sure that it's correct. But often there are these kinds of optimizations that you just can't make, or that you neglect if you're doing incremental code. And so I just switched it over to a batch updating thing. And that reduced the processing time for like this stage from around 2.5 seconds down to around, depending on how you calculate it, somewhere between 100 milliseconds and like 500 milliseconds or 800 milliseconds. So like a factor of 3 speed up. And that helped.
And just for reference, that's a significant increase as far as other like. Well, I don't know what the relative to what I guess is I don't know, but that sounds significant to me.
Yeah, it basically like doubles the speed for processing a new block overall when there are transaction chains present in the block. And transaction chains are not actually present at that high of a level except in stress tests when there are organic transactions. If you had 32 megabytes of organic transactions, then there would mostly be smaller chains or length 1 chains independent. So this issue really shows up when we're doing stress tests, and it also shows up in the worst case scenarios if somebody's spamming the network. So it's completely relevant for determining block size limits, and it's completely relevant for stress tests, but it's not actually relevant for real world throughput in sustained situations that actually involve um, um, people sending transactions to actually buy stuff. So it's a weird thing because it does actually matter because it's the worst case scenario, and it also shows up in the benchmarks. But it's not the typical or normal case scenario. So it doesn't help with like the 200 kilobyte blocks that we're getting right now, but it does help with the 32 megabyte blocks that we get if we're trying to stress the system.
And I imagine it's possible someday that someone will come up with a use case that, does require plenty of those long chains, all the time, in which case then the work you're doing now will not just be, you know, nice to have for preventing worst case scenarios. It might actually end up being applicable to organic use, right?
Yeah, that's a good point, and it's definitely true, and that's also one of the reasons why I've been working on it. So even though for block validation, it doesn't really matter if we're um, that fast for typical blocks, it does matter for the safety limits that we can set on chain length. Right now, we've got an issue in which the fact that a chain can only be 50 transactions long means that businesses have to program their code to never make transaction chains that are longer than 50 transactions, or to somehow otherwise deal with this issue. And I've seen several different Bitcoin application developers run into this issue where they have, for example, like the most prominent is Satoshi Dice. They have a user who comes in to play their Bitcoin game. They play a few rounds. They start getting into the swing of things. They say, "Oh, this is fun. I'm going to do more." And then they play a bunch more rounds. And then finally, they play the 50th round, and that creates a transaction. Actually, I think it's the 25th round because it's 2 transactions per round. So they play 25 rounds and they get a 50 transaction chain. And then they try to play the 26th round and it just fails. And it says, "Sorry, you can't do that. Please wait 10 minutes for one confirmation," or whatever, something like that. And that ruins the game experience. And people don't wait 10 minutes, they just do something else. And so that ruins Satoshi Dice's business case. It also has shown up in the mainnet .cache or whatever. There's a read.cache's developer has been trying to build a JavaScript library for building web wallets that would be easy to use. And actually, I think both read.cache and the mainnet project have run into this issue where when you're doing upvotes on articles, you also get chains of transactions. So if you're reading articles and you interact with 50 articles, or if you make 50 interactions with articles, maybe you're upvoting on comments, and you do that within the span of one block interval, you can also hit that 50 transaction chain limit pretty easily. And that, like, whenever this happens, usually there's a way around it. There's a way to set up multiple UTXOs in your wallet and alternate between UTXOs and create 5 chains of 10 transactions each instead of 1 chain of 50 transactions. But it makes all application development slower because the programmer has to think about those things. It can't just pick the most obvious transaction or pick the most obvious UTXO and maintain a small set of UTXOs in the wallet. And yeah, this batching of transactions is not a perfect fix to the chain transaction performance issues. It only affects the performance in one section of the code, but it probably is enough to allow us to safely increase the limit to, say, 100 transactions per
Okay.
chain.
And the section of the code you're talking about, that's the one where we're talking about block processing and
removing transactions from mempool after a block arrives, the remove for block function.
And is that the majority of the work you've been doing on the unconfirmed chain limit, or have you worked on any other locations where it's a bottleneck?
So I did this remove for block stuff, like finished it about a week ago, or opened the merge request about a week ago. And then I started to move on and rewrote the whole mempool package calculation code from kind of scratch. And I sort of finished that, like, I don't know, about 8 hours ago.
Very cool.
So yeah, I'm kind of getting a little bit excited about that. And I got this new algorithm working with the create new block, get block template part of the code, where it assembles a bunch of transactions into a block. And for a, let's see, for the 26 or 25 transaction scenario, where the chain sizes are average 25 transactions, the old code was taking about 3 seconds to assemble the transactions into a block. And the new code that I wrote does the same thing in 0.4 seconds. So that seems like a bit of an improvement, and that's also not the worst case scenario. The worst case scenario is 50 transaction packages or larger. And yeah,
In which case the gain would be larger?
Yeah, the gain is larger. I also tested with 85 transactions per package. And the old code was performing at about 12 seconds for 85 transactions per package for a 32 megabyte block to assemble it. And the new code is 400 milliseconds, which is basically exactly the same as for the small packages. So the new code is what we call big O1 per transaction, or big O(n) per block. It doesn't matter how long the transaction chain is. The new code will operate at the same speed no matter what. And that basically means that we can get rid of the transaction chain limit altogether once, assuming this code doesn't have any bugs and gets merged into BCHN and into other mining nodes that are in common use. So yeah.
Very cool, and that is exciting. I'm sure it might be a little tough for some people to follow along, but I hope they can at least appreciate, given the experiences you've relayed here, how much work.
I have a whiteboard, so if they're having difficulty following along.
It just shows that there's so much work involved in quote unquote solving scaling, or even if it's not one thing to solve, there's a huge amount of work, and it's often you don't know what you're going to find, do you?
Yeah, I mean, I thought I was going to be able to solve this network propagation problem by just adding XThinner and making the blocks smaller. But it turns out there's this other delay caused by the CS main lock and block validation, and that makes it so that I need to actually fix this other problem in order to fix that problem. So yeah, it's and I think one of the big issues that we've been having in this optimization work is that we haven't had good benchmarks. We haven't had good test setups for simulating or for generating large blocks and measuring the performance of that. And what we've kind of done in the past was we've just done network-wide stress tests. But we haven't done those very often, partially because they're disruptive, and also partially because it was mostly the BSV crowd before they slid off that was initiating those. And a lot of what I've been doing over the last year is actually creating good test setups for generating transaction spam and testing block propagation, testing transaction validation, testing everything else at the limits of performance. So I think that that's really what's allowing these bottlenecks to be pinpointed and fixed. It's having the right test setup. It's having the system for reliably, repeatably, and cheaply replicating the scenarios that we would experience in a network-wide stress test.
Very cool, and that sounds to me like the sort of work that not everyone knows is happening, or even knows needs to happen. So I appreciate your sharing that. Just out of curiosity, are those tools something you've made available if anyone was curious about them?
So the easiest to use and most useful tool is a script that I call ptp stress test.py, which is in BCHN merge request 442. It's almost added into BCHN code. It's like, I think, I don't know, it's been very close to being merged for a while. And that allows for somebody to generate transactions at a rate of about 30 to 80 transactions per second per CPU core, and to make a network of, say, 4 or 10 or 20 nodes all on one machine that connect to each other. And all of the nodes generate transactions and send transactions to each other. And then eventually a block is propagated and it measures the propagation speed of that block. And so that one is pretty mature and pretty easy to use, or fairly easy to use for developers. There's also another system, which I call the remote stress test framework, which does something very similar, but instead of using a bunch of nodes on a single machine, it uses a bunch of machines and allows you to create a fully networked system in which you have, say, 4 computers, each of which are running 10 nodes, and you send, you make connections between each machine in like a round robin fashion, so that machine 0, node 0 connects to machine 1, node 0, which connects to machine 2, node 0, which connects to machine 3, node 0, which connects to machine 0, node 1, etc. And so you can make these chains or these networks as long as you want, while still requiring a actual network hop in each case. And the key thing that I added to the remote stress framework is that it allows you to, at the kernel level, use the Linux NetM module, network emulation module, to inject packet loss and inject network latency into those connections. So you can actually really accurately simulate, or almost completely accurately simulate, a worldwide network all on your LAN.
Very cool. Yeah, that sounds invaluable.
Yeah, so I've been doing a lot of testing with that, and that's how I found that when you get to 5% packet loss, you get limited to about 200 transactions per second peak, and like reliably about 150 transactions per second. Yeah, and so that's working. I've got like a test setup of 4 servers at my data center that each have 40 cores and 64 gigs of RAM, and like a 4 terabyte hard drive each, and then big SSD. And so I'm planning, these machines are available for any BCH developers to use. If anybody who is working on related stuff wants an account, they can just talk to me and send me their SSH copy, and I'll show them how to use it. I don't yet have the remote stress framework running in a easy enough to use fashion for it to be easy for the developers to use. So, but if anybody wants to do some testing with it, I can show them how to use it and show them what things break and how to fix those bugs, or how to work around them.
Very cool. We'll make sure to include in the description, however it is that you'd like to be contacted if someone watching or listening would like to take you up on that.
Yeah, email is fine, j@toom.in. Telegram is fine, jtoomim. You can ping me on Reddit. You can find me on VCHN Slack. Please don't show up at my house.
Yeah. You heard it here. Please do not show up to Jonathan Toomim's house. So before we wrap up, I would like to have you talk just a little bit, because we talked so much about how the network affects everything, but you did run a test somewhat recently that showed what is possible when there is no networking bottleneck. Is that right?
Yes, that was an early version of the, like, are you talking about the YouTube video I did?
Yes, that's right.
Yeah, so that was an early version of the script that became P2P stress test, and that was running on Bitcoin ABC, and that was running with a simpler type of transaction, a 1 input, 1 output transaction. And under those circumstances, I was able to get 3,000 transactions per second of throughput. Nowadays, I'm running with 2 input, 1 output, or 2 input, 2 output transactions, which are more complicated. And so I'm getting about 1,500 transactions per second on my desktop computer with like the same resources, same hardware. And that's not because
without any simulated latency.
Without any simulated latency, exactly. And I can also get those throughput rates on the remote stress framework as long as I don't have any simulated packet loss. The latency is actually not a significant problem. Latency slows things down a little bit, but It's only when you have packet loss that you get a reduction in the effective bandwidth. And actually, it's only when you have both packet loss and latency. When you have packet loss, that decreases what's known as the congestion window size for TCP. The congestion window size is the number of packets that are allowed to be in flight between the sender and the recipient at any given time. And when the congestion window is 5 packets and latency is 0, the amount of bandwidth you can get between those two nodes is infinite. When the packet loss, or when the congestion window size is 5 packets and latency is 100 milliseconds, that means you can get 50 packets per second, which ends up being something like 75 kilobytes per second, which is not that much. So the higher the packet loss is, the smaller the congestion window, the higher the latency is, the longer it takes for you to send each congestion window. And so that pair of issues is what limits throughput, what limits bandwidth with TCP.
Gotcha. Well, thanks very much, Jonathan. It's been a pleasure speaking with you, and I appreciate your taking time to come on the podcast.
Oh, my pleasure.
And to our listeners, thanks for tuning in. Make sure to subscribe, hit the bell icon on YouTube if you'd like to be notified about new uploads from Bitcoin Unlimited. Thanks again.